Okay. Can everyone hear and stuff? Yes, no, maybe so. Okay. So I thought we would start off with just like a tiny bit of review of what we did last time. And then I put some warm-up problems on Moodle that you guys can find. So I thought that after we did a couple of things related to what we did last time, I was going to split you guys into breakout rooms for a little bit and do these warm-up problems, and then we would come back and like do the new stuff or whatever. So that's kind of our sequence of events. So the warm-up problems, like I said, they're on Moodle. You don't really need to find them now, but just find them in a little bit. They're like that. But before we do that, let's kind of review some of the stuff we did last time. We talked a lot about, how to write down sets and this kind of stuff. And then we ended with sets of real numbers and interval notation and intersection and union and stuff like that. So what I want to do is just do a couple of examples that kind of tie all that together. Like we did intersections and unions for like sort of silly made up sets, but we never did them for intervals. So I want to make sure and do that real quick. And then we'll do this warm up problems, and then we'll move on to kind of what we're doing next. Okay, great. So let's see, maybe we'll say, so let's say we've got this set here, which I'll say is the closed interval -1 to 3, and let's say it's open on the side of 3. And then we want to union that with the open interval 2 to 5, and let's say it's closed on the side of 5. And so remember that to be inside of this union means that you are inside of this closed interval or this closed interval. So we could maybe say that like this. So X is inside of that union of two closed intervals if X is inside of -1 to 3 or X is inside of 2 to 5, where we're like including the endpoints or not, like depending on our notation there. And we could like turn these from intervals into kind of inequalities. Notice that X being inside here, that's the same thing as saying that X is strictly bigger than -1. Bigger than or equal to -1 or less than -3. But to be honest, at this point, the best thing to do is like to draw a picture and see what's happening geometrically. So that's maybe what we'll do now. So, but the picture is just a number line because we're just talking about sets of real numbers. So I'll go ahead and put 0 on the number. Then maybe we'll put the half open interval -1 to 3 in this color. So that means over here we would go to -1. Let's say this is -1. And then the fact that we have a bracket there means that we include that. And as a graph, we include that by putting a closed circle. And then we go over here to 3. Let's say maybe this is 3. And then the fact that that's a parentheses means we do not include that. So we put an open circle and then we shade between. So this right here is this interval, which is closed -1 to open 3. Now let's do the same kind of thing for this guy right here. So that would be open 2. So let's go ahead and put maybe 2 would be right here. And then what I'll do is I'll put this just a little bit above so it doesn't get too messy. But it's, you can think about it being on the number line. So I'm not including 2, and then I'll put 5 way out here, but I am including 5, given that I have this bracket. And then it's going to be everything in between. Great. But now, if I want to think about what's happening when I really join these together, the or conjunction like joins these two things together, it's either here or it's there. So that means you can really just simplify this down into one piece. And that one piece would be -1 to 5, right? And so, and you can see that by just shading everything that's shaded in total. So maybe if we were to shade everything that's shaded in total, we would have a closed circle here, a closed circle way over here, and then everything in between would be shaded. And that's going to give us the union of these two. So in other words, we can simplify the union of these two down to just this closed interval -1 to 5, like that. And so you can do it with like some compound inequalities like I was starting to do here. Notice that this means that x is strictly bigger than 2 or less than or equal to 5. And then you have this or between them. But now notice when you put that together, you have x is between -1 and 5. You get the same kind of thing, but I think drawing the picture, it's just faster and kind of more intuitive. Okay, so a simplification of these like union of intervals is like a sort of important thing. It's not something exactly that we did last time, but it kind of follows from a couple of the parts of what we did last time. So I wanted to make sure to do an example that was precisely like this. Okay, good. Now let's maybe go ahead and switch this up a little bit. I'll keep the same sets, but I'm going to change this union to an intersection. And then we'll look at what we get. So I'll change this union to an intersection, which means none of this is true anymore. So let's erase all of this. And then recall that if the union is like the English word or, the intersection is like the English word and. So that means x is in the intersection of these two. If x is in -1, 3, and x is in 2, 5, where, you know, we have the appropriate brackets and parentheses or whatever. Sorry, I missed a, there we go. So this is more like an and statement is more restrictive than an or statement. You have like, yeah, anyway. So I would go ahead and do the same kind of thing that we did before, except you're going to interpret the picture a little bit differently. So let's put this picture up on the board just real quick again. So we have -1, 2, 3, and 5. Those were all important numbers here because those are the numbers that are endpoints of these intervals. And then this one that's in like this peach color. So I'll again shade that in peach down here. Maybe I'll put that above. So that's going to be this closed circle up to this open circle. And then this one in purple, I'll maybe put that one below. So that's going to be this open circle up to this closed circle. But now instead of joining these things together and looking at everything that's completely shaded by both, we want to look at only the parts that are shaded by both colors, right? So instead of putting all of the shading together, we only want to look at the parts that are shaded by both the peach and the purple. So if we were to do that, we would see that, well, we cannot include 2 because we've got an open circle here. We cannot include 3 because we have an open circle there. But anything between 2 and 3 is okay. Because if you're between 2 and 3, then you're definitely between -1 and 3. And you're definitely between 2 and 5, which means you are definitely in both. But now we can transport that back into interval notation. So that's going to be all numbers between 2 and 3, not including 2 and not including 3. So this is going to be this open interval on both sides, 2, 3. Cool. All right. So now I want to maybe do one more little example before we kind of split into groups and do these warm-up problems. And that is Well, sometimes you cannot make this simplification, you know, for better or worse. So let's say we wanted to write this following set in interval notation. And so let's say the set is defined like this. So let's say it's all numbers x where x is not equal to maybe 3. So we want to write that in interval notation. So I think working through the graph is always something good to do. So if we work through the graph, well, how would you graph the set of all numbers except for 3? So everything except for 3. And so we use this kind of strategy of like putting 3 on the number line, putting an open circle around 3 that says, hey, we're not including 3 in this set, and then shading everywhere else. So I'll shade all the way to the left, and then I'll shade all the way to the right as well. So that's kind of a picture version of including everything except for 3. So I'll go ahead and like underline that in green just to point out that's the set that I'm meaning right here. But now that I have this picture version, I think it's a bit easier to write down the set in interval notation. So we just start way over here to the left and start and see, well, what's the smallest number in this set? The smallest one. Well, there is no smallest one, right? Because we've got this arrow pointing infinitely in this direction. So that means the smallest number, it's minus infinity, but that's not really a number, right? So we just put the minus infinity there. And then we work towards the right until the set stops. So we notice that the set stops at 3, so we put a 3 there and another parentheses. But then the set picks up again at 3 and goes forever to the right, and then we put a union of those together. So that's how you would write this in interval notation. So notice it's this union of these two intervals that can't really be combined. We would say that they're disjoint because they don't include any of the same numbers. If they include the same numbers, we can simplify them like we did in the first example, but these don't include any of the same numbers, so we can't simplify them. It's just a union of these disjoint intervals. So we end at that. So it's going to be minus infinity to 3, union 3 to infinity. And that's how we talk about like this set right here, which also maybe has this name up here if we were to write it in set builder notation. And this will be important like later when we talk about domains of functions or whatever, which is like super important in calculus and stuff. Okay, let's maybe do one more and then we'll go into breakout rooms or whatever. So it's going to be similar to this one right here. Okay, so let's say the heading is the same, so write an interval notation, and then let's say the set is the set of all x that satisfy the following rule. So let's say x is bigger than 2, maybe bigger than or equal to 2, and x is not equal to 10. Good. So this is going to be like the same sort of idea like this one down here. I like to work through the graph each time. I mean, that might be a step that you skip at some point, but you know, don't feel bad if you always want to draw the picture. I think it's really good to involve like the geometry of the whole situation all the time. So let's maybe draw a picture. So we've got a number line, and the strategy will just shade in everything that satisfies both of these rules. So x bigger than or equal to 2, that means we include 2. So we've got a closed circle there, and it's going to be bigger than 2. And that seems like it's going to go on forever and ever and ever, but this fact right here that x cannot be equal to 10 means we need to go over here to 10 and take it out of the set. And we do that by putting an open circle there. So this would be like a way of drawing that. Is the green contrast enough, or should I use something else? It's okay. Medium. I'll play around with it. Okay, so just to kind of, this is what's going on. Okay, so good. Now we take this picture. Notice that everything that is shaded is either bigger than or equal to 2 and not equal to 10. We think about this open circle as just like pulling that single point out of the number line. But now to write this in interval notation, we do the same kind of thing that we did before. We start to the left and we write the very smallest number that's in the set. But in this case, there is a smallest number. It's the number 2. Then next, we move right until we see the first number that's outside of the set. So if we move right, we notice that 10 is the first number outside of the set. We have to put an open circle there because we don't include 10. But then we put a union. We have to pick up back at 10 and then roll all the way to positive infinity. So I think maybe a theme is appearing whenever you have to pull these single points out of sets. You have this like kind of setup right here where you have, you know, not including the number and also not including the number with the union in between. So that's like what happened down here too, right? So that's a pretty typical way to have to pull these points out of a set. Okay, cool. All right, so I'm going to go ahead and split you guys into the breakout rooms. Maybe like, let's see. Maybe I'll put like 3 people in each room. So there'll be one room with 2 people. So just find on Moodle this warm-up thing. I would say maybe that's the best way to do it. And then I'll come around to some of the rooms while you guys are doing this. I don't know if I'll have time to come around to all of them. But if you have a question, there's a way to like ask me to come into your room or whatever. So did everyone find the warm-up sheet? Okay, cool, great. So I'm making rooms right now. So assign 16. Okay, so let's maybe look at a couple of these before we move on, maybe the last 2 from the first bullet point, and then we'll like pick one from the second bullet point as well. So this number 3 was to try to simplify the intersection minus infinity to 4, including 4 intersect 0 to infinity, not including 0. Okay, so we can move through a picture of this on a number line. Maybe we'll color code this. So I'll say that this part is this green and this one will be red. And so we can make our number line. There are only 2 numbers that are important on the number line because the infinities are just kind of like far to the left and far to the right. So we'll put those 2 numbers 0 and 4 here. Now let's graph this green one. Maybe I'll do that like above the number line just to leave myself some room. So let's see. This green one is going to be everything negative infinity to 4. So I'll shade in 4 and then shade backwards. So it's everything less than or equal to 4. So it's going to be everything back in that direction, kind of upper bounded at 4. And then for the other one, so it says not to include 0 because of the parentheses there. So we'll put an open circle and then everything bigger. Great. But now if we want to intersect these, we want to look for things that are shaded both green and red. So the things that are shaded both green and red, we could write in blue like this. So here we could, it does not include 0, but it will include everything up to 0. And then it does include 4. And then it's going to be everything in between like that. So that would be the shading or the picture of this set. But now if we wanted to write that in interval notation, it would be open interval on the left by 0 and then closed on the right by 4. So we would get something like that. Good. And then maybe like just as a little bit of a bonus, well, what if we had the union there instead of the intersection? So remember, the union is like an or statement. So we want to see if it's in here or in here. But notice that every real number satisfies that, right? Yeah. So like the green extends infinitely back that direction. The red extends infinitely into the right, and so you would end up shading the entire number line. So the answer for the union would be, well, we could write it one of two ways, minus infinity to infinity, or we could write like all real numbers also. That would be like another way to write it. So this would be interval notation. This would be like, I don't know, using our stuff from yesterday or day before yesterday or whatever. Okay, so let's go ahead and look at this next one, I should say. So this is going to be minus infinity to 0, intersect 1 to 5. Let's see, did I get the closures and stuff right? Yeah, so we do not include 0, but we do include 1 and 5. So we could do the same kind of thing. So important points here are going to be 0, 1, and 5 because, you know, we don't need minus infinity because that's just the idea of going forever in that direction. So let's go ahead and put 0, 1, 5 on the number line. We'll graph this first one in green again. So that means we need to not include 0. So open circle and then everything to the left. So it would be like that. And then let's see, let's graph this one maybe in red. So I'll do it below. So we do include 1, we do include 5, and then everything in between 1 and 5. And now, again, it's an intersection. So it has to include, so if it has to be in this set and in this set. In other words, we want to look for everything that's shaded both green and red. But notice there's nothing shaded green and red, right? So there's nothing shaded green and red. So that means there are no numbers that satisfy this rule. And so generally what we would say here is that this is equal to the empty set. In other words, there's like no solution here, or we could write this. This is like the symbol for the empty set. So maybe we'll do this third one from the second bullet point 2 real quick before we move on. That's like taking something in set builder notation and then rewriting it in interval notation. So let's see, we've got x such that x is less than 3 or x is bigger than or equal to 2. Okay, so again, let's see what that restriction is going to be. So we can say this right here, this x is less than 3 will shade in red. So notice that means we go over here to 3, we put an open circle, and then we shade everything backwards. Great. And then let's say this x bigger than or equal to 2 will be in green. So that means we go over here to 2, we put a closed circle. So maybe I'll just put it on the same graph this time, and then we shade everything forwards. And then since we have an or statement, we want to look for everything that's completely shaded, either shaded green or shaded red, it doesn't matter. But notice that because of how these overlap, everything is completely shaded, the whole real number line, right? Goes infinitely back in that direction, it goes infinitely up in that direction. So this is like similar to this other one that we looked at kind of as a bonus. That's like minus infinity to infinity. That's how we write that in interval notation. Or we could write that like our fancy real numbers, or verbally it would be all real numbers. Kind of, it's all okay. Okay, cool. So, hopefully that was helpful. Just kind of, a bit of practice related to some of the stuff that's going to be on the homework, and like kind of an extension of what we did last time. So maybe the next thing that I want to do is move on to talk about like basic arithmetic rules in the real numbers. So I'm not going to do all of the details. Like the addition is commutative. So like A plus B equals B plus A, because that's like sort of well known or whatever. But I will do some of the rules. So let's maybe get rid of this. And then we'll do some examples. Okay, so maybe we'll say, we'll name this arithmetic properties of the real numbers. So we'll write it like that. So maybe we could do things like this. Number one would be when are two fractions equal to each other. So obviously this doesn't have to happen in real numbers. This could happen in rational numbers. But, we'll just do it in real numbers. So we have A over B is equal to C over D. So that's going to be if AD equals BC. So that's like kind of written one way with fractions and one way without fractions. So this is not mind-blowing if you just think that this is the same thing as saying like 1/2 is equal to 2/4, right? And why is that true? That's because if you multiply the 4 up here, you get 4 times 1 is the same thing as 2 times 2. Essentially what this is saying is you can cross multiply. So just with numbers, this is not a big deal, but for like solving equations, this is like particularly useful. So maybe useful to solve equations, which we'll like be getting to super quickly, because often you'd want to solve equations that have fractions, but it's harder in the fraction form than it is in the equivalent form that doesn't involve fractions. Like let's say we wanted to solve x plus 3 over x equals 2 over 9 or something like that. Well, solving this just as is pretty tricky, but this rule right here about equivalent fractions makes it not so tricky, because we can just like multiply up on both sides or cross multiply or whatever. So I won't do that because that's something we'll get to or whatever. But that's why this like seemingly innocuous thing that has a really like trivial example when it comes to putting numbers in there is actually like really important for what we're getting at. Okay, so and then next, let's just recall that if you need to add fractions, you have to find a common denominator. So if you have A over B plus C over D, now you can like sort of quickly find a common denominator by multiplying this by D over D to give a denominator of BD, and then this by B over B. So what it ends up being is like AD plus BC. But this is often not optimal. Sometimes there's this lowest common denominator or whatever. But I mean, that's sort of neither here nor there. Like if we wanted to do 1/4 plus 1/6, right? So our common denominator would need to be 12. So we'd have to build this up until it had a denominator of 12. We could do that by multiplying by 3 over 3. We would have to build this up until it had a denominator of 12. Excuse me. That would be multiplying by 2 over 2. Notice we don't change anything because we're multiplying by 1 each time. It's just 1 in a different form. But that changes this first bit to 3 over 12. And that changes the second bit to 2 over 12, which means you can add the whole thing up to 5 over 12. Which, you know, this is a lowest common denominator. It's more optimal than just like taking the product or whatever. And then again, with numbers, this is like maybe not so mind-blowing or whatever, but, you know, later we'll be like adding together rational expressions with like variables and stuff. So really, you know, see the future for when we need to remind ourselves that it's really the same thing, just with more general objects. Like what if we wanted to add 1 over x plus 1 plus 1 over x squared minus 1? We would need to do something similar there, find common denominators and stuff, but it's the same game as it is in fractions. But, you know, like I said, we'll get there. That's just kind of where we're getting. Okay, cool. So let's see. Next, maybe, yeah, so I think first, second, so these are all have to do with fractions. Maybe next, just as a quick reminder, the distributive rule. So this would be 3. So let's just recall that if you have real numbers A, B, and C, you could take A times B plus C. That's going to be the same thing as AB plus AC. So like, for example, notice if we take 2 times 6, well, that's like kind of obviously equal to 12. 2 times 6 is 12. But we could also do this as 2 times 4 plus 2. We could split the 6 up into 4 plus 2, but that's going to be 8, which is what we get from doing that distribution, and 4, which is what we get from that distribution. But notice 12 is 8 plus 4. I mean, this is like, I have a kid that's in 4th grade or whatever, and this is how they have kids like learn to multiply now. They like break it up into the distributive rule and stuff. I mean, I tell them that it's the distributive rule, but I don't know that all parents tell them it's the distributive rule because I'm a crazy person. Okay, and again, this is not like mind-blowing at all when it comes to numbers, right? But, you know, having a good recollection of these basics allows us to move to more general objects later when we have to. Like, what if we wanted to do x plus 3 times x minus 2? We wanted to do something like that. You'd have to do this distributive rule twice, really, in this case. You would take, let's see, you would take x plus 3 and multiply it onto x, and also take x plus 3 and multiply it on negative 2, and then do a distributive rule inside of that. And like I said, I mean, we'll get to that or whatever, but, you know, that's some sort of motivation for why we need to recall these things like super carefully. Okay, then maybe one more quick thing before we just have like a bunch of examples, and that would be some rules about the exponent rules. So let's look at that. So exponent rules. So this would be maybe number 4. Cool. So maybe there are a bunch that go along with this. So let's say the first one is if you have a to the x times a to the y, that's the same thing as a to the x plus y. So if you're doing multiplication down here, it turns into addition in the exponent. And we could like do a pretty similar like little example involving numbers. that will extend to something that's going to be more important a bit later, like maybe a little example involving numbers would be something like 2 to the 3 times 2 squared is the same thing as 2 to the 5. Well, if you take 2 to the 5th power, you get 32. But now 2 cubed is equal to 8. 2 squared is equal to 4. So that's 8 times 4 is 32. So we're getting the same thing just by different calculations, right? Here we're doing the product after raising the exponent, and here we're doing the product before raising the exponent and like multiplying those, adding those exponents. Okay, so maybe that's our first exponent rule. Our second exponent rule would be like this, the companion of this, which would be division. So if we have a to the x divided by a to the y, so that's going to give us a to the x minus y. So multiplication turns into addition in the exponents. Division turns into subtraction in the exponents. So maybe the most important thing to notice out of this is that if you have 2 to the negative 1, that's going to be the same thing as 2 to the 0 minus 1, which is 2 to the 0 over 2 to the 1, which is 1/2. And there we use the fact kind of that anything to the 0 is equal to 1. That's like an important fact to recall. So fact. A to the 0, anything to the 0th power is equal to 1. Okay, so this is the kind of product rule for exponents. This is like the quotient type rule for exponents. Now maybe like over here, we'll look at a couple more. What if you take an exponent to an exponent? So let's see that. So if you have a to the x to the power of y, then you do multiplication. So this is going to be a to the x times y. So essentially when you're combining these things involving exponents, you drop down one level of operations or whatever. So the multiplication turned into addition, the exponentiation turned into multiplication. So, I mean, we could do a little number example for this as well. I don't know how illuminating it is, but maybe like we could do 2 to the 2 to the power of 3. So on the one hand, that's equal to 2 to the 6 by this rule up here. I mean, you can see the numbers get big pretty quick, right? So then 2 to the 6 you can check is equal to 64. But notice that's the same thing as 4 cubed. But then you can also check that 4 cubed is also 64. So, it works. It's kind of the important part. Okay, then there's one more thing, and that is, what if you have fractional exponents? So that's going to be important as well. So maybe this will be the 4th bullet point on the exponent rules. So if you have a to the x over y, so that's going to be equal to the y-th root of a to the x, or it's going to be equal to the y-th root of a all to the x power. You can do that in any order you want. So let's do a little example of this because it's maybe worthwhile. If we do 4 to the power of 1 over 2, so that's going to be the same thing as the square root of 4. Notice usually with a square root, you don't put the 2 there, but maybe we'll put it there for good measure. So the square root of 4, but remember the square root of 4 is like the special number that when you multiply it to itself, you get 4. So this is going to be equal to 2. And then, let's see, we could do maybe 8 to the power of 2 over 3. So using this rule right here, that is going to be the third root of 8, and then you need to square it. So again, the third root, so that's going to be the special number, so that when you cube it or when you multiply it to itself 3 times in total, you get 8. So notice 2 times 2 times 2 is 8. So that means the cube root of 8 is equal to 2. So this is going to be 2 squared. Here, I just want to notice that I replaced this cube root of 8 with 2 because that is the cube root of 8. And then you take 2 squared and you get 4. Great. Now, sometimes these don't simplify all the way and you're left with radicals in the end, and that's like okay as well. Like if sometimes you'll be left with something that looks like the square root of 2, and there's no way to write the square root of 2 as something simpler, right? There's a way to write the square root of 4 as something simpler because it's a perfect square. But if you don't have a perfect square in there, there's not a way to write it simpler. So generally we just leave it like that. Okay, so maybe one last thing to look at before we do some examples is the order of operations. Okay, so let's see. Let's recall that real quick. Oh, and I got my fancy microphones working this time. Does the sound better than it was last time? I don't know if anyone can tell. Yeah, they're out of frame, so you can't really see them. Okay, so the order of operations. So let's say you have a bunch of numbers or symbols or whatever, and you're combining them together with different arithmetic operations. Addition, subtraction, multiplication, division, exponentiation, all that kind of stuff. Well, I really like how the book puts it. It's just like, as a society, we have decided what order we're going to do these operations in. There's nothing like really special about it. We've just decided that we're going to do it in this in this order. And that's so that we all get the same number in the end, right? Like if we had different choices of which order we did the operation in, we would get different numbers and it wouldn't be good. So the order that we've chosen is that we do parentheses first. And then I really want to notice that even more generally than parentheses is this notion of grouping. So things can be grouped without like obviously being in parentheses. Like if you have a fraction and there's a bunch of stuff in the numerator and then maybe just one thing in the denominator, you want to think about this bunch of stuff as being inside invisible parentheses. That being inside of the numerator of the fraction or even being inside of the denominator of the fraction is like being grouped together. And so that goes in this first round of doing parentheses. Okay, great. And then after simplifying the parentheses, you do exponents. And then I want to like point out that exponents also mean taking roots. So maybe we'll put this in quotes, in parentheses. So, and roots. So exponents and roots are the same thing. And, by our last exponent rule, we kind of saw that, right? So 4 to the half, that would be the exponent version of the square root of 4. Okay. So parentheses, exponents. And then the next thing is multiplication and division. And then the fourth one is addition and subtraction. And you can do these in any order as long as you're like careful about viewing the addition and subtraction as, being with respect to like positive and negative numbers and stuff. So yeah, like for example, if you wanted to do, so again, like in my kids' homework or whatever, they like try to trick them like this all the time. If you want to do something like 3 minus 4 plus 2, right? You don't do that addition of 4 plus 2. Like you don't do 4 plus 2 equals 6, 3 minus 6 equals -3. That doesn't work. You want to view this as -4. So you do -4 plus 2 is like -2 or whatever. Or you really just work from left to right. So -3 minus 4. So that's -1 plus 2, which is 1. So when they're kids, they just teach them to go left to right. But if you know about negative numbers, you can really do it in any order you want, as long as really what's happening really is you're exchanging all of the minus signs for a plus negative version of that number. But it's all kind of the same or whatever. Okay, great. So order of operations, I don't know, like there's mnemonics to remember these, like please excuse my dear Aunt Sally and some other ones you guys probably saw in the past. Okay, great. So let's do some examples maybe. Maybe we'll sort of do this in the round of like, I'll do one and then I'll put one on the board and you guys can try it and we'll repeat that a few times. And then we'll essentially be out of time, I think. So let's maybe say this one is first. So 2 times 3 minus 4 minus 1 all over 2 squared plus 1. Okay. Actually, maybe I'll just let you guys try this for a minute or something. We're not going to break into rooms or whatever because there's only one problem at a time. And then we'll look at the simplification here and make sure that we're all on the same page for this stuff. Okay, so we want to do parentheses or grouping first. Notice there are 2 groupings happening here. There's this one right here, which is an actual grouping by parentheses. And then there's a second grouping, which is happening down here because it's a bunch of stuff in the denominator. And so we'll go ahead and simplify both of these first because you can think about them both as being grouped together or both as being in parentheses. There's like phantom parentheses around this because it's grouped in the denominator. Okay, so 4 minus 1, that's like 3. And then what do we have? 2 squared plus 1, so that's going to be 4 plus 1, so that's 5. Now let's go ahead and rewrite this. Maybe while we're at it, we can say this 2 times 3 is equal to 6. So that's going to give us 6 minus 3 over 5. 6 minus 3 is 3, so we get an answer of 3 over 5. And then you might maybe want to put this fraction in lowest terms, but there's nothing you can do. It is in lowest terms already. Okay, so let's look at maybe one that's a little juicier. So let's say this 2/3 minus 4/5 over 1 minus 4/3 squared. All right, so let's go ahead and look at this. So again, we have some grouping going on. We've got parentheses here, but this isn't like a real parentheses. We're just squaring the fraction 4/3. That's essentially what's happening there. So that's more of exponents. But the phantom parentheses we have are the fact that we have bunch of stuff in the numerator and bunch of stuff in the denominator. So that's really the simplification we want to make. First, we want to make the numerator and the denominator as simple as we can before we do anything else. So let's see. We've got 3 as a denominator and 5 as a denominator, and I should say in the denominator of the numerator. So we would probably like to find a common denominator. These are, the word is relatively prime, but the lowest common denominator is just their product. So we can multiply by 5 over 5 here. We can multiply by 3 over 3 here. That's going to do a transformation into numbers that have a common denominator. So while we do that, let's go ahead and take this and square 4/3. So if we square 4/3, that's just 4/3 times 4/3, or 16 over 9. 4 times 4 is 16, 3 times 3 is 9. So let's see, now we have 10 over 15 minus 12 over 15. Is that right? Yeah. And then over 1 minus 16 over 9. Now we're totally set up in the numerator to add those fractions together because they have a common denominator, but we're not set up in the denominator to do that because here we have 16 over 9. Here we have the number 1. So we'd like to rewrite the number 1 so that it has a denominator of 9. But, I'm just going to go ahead and do that all in one step and say that's the same thing as 9 over 9. Notice I just took this 1 and replaced it with 9 over 9. That's like the classic way to rewrite 1 with any denominator you like. And now we're good because we have this numerator and the denominator are both combinations of fractions that have common denominators, and we can really go at it. So let's see. We've got 10 minus 12, so that's going to be negative 2 over 15 over... So 9 minus 16, that's going to be negative 5 over 9. Then the next thing that we can do is see that we've got negative in the numerator and in the denominator, so we can take those and cancel them, right? 2 negatives make a positive. It doesn't matter if we're multiplying or dividing. And then we can use the fact that when you divide fractions, you have to multiply by the reciprocal. So that gives us 2 over 15 times 9 over 5. Is that right? Yeah, that's right. Good. But now that we're set up like that, we can just multiply straight across. So let's see, what do we get if we multiply straight across? So 2 times 9 is 18. And then 5 times, actually, no, let's be smart about this. Now we can simplify before multiplying across. So notice we can write this 15 as 3 times 5. Then we can write this 9 as 3 times 3. Then we can take this 3 and cancel it with this 3. And then we have like easier arithmetic problems to do. So we'll do 2 times 3, so that's going to be equal to 6. And then 5 times 5, so that's going to be equal to 25. And because we did that simplification ahead of thank you. Yep. Yeah, so this should be 7 over 9. Let's see, what does that do? That puts a 7 right here, right? And so we'll have 35. Thank you so much. It happens, right? Sorry. Okay, cool. So let's see. We got like 6 minutes. I'm going to do one of these ones that's like a little more complicated, and then maybe we'll call it. So I'm going to get rid of this. Okay, so let's see this one right here. So this looks kind of scary, but it's really not that bad. We'll do the square root of, and then inside of that, we have the square root of 5 minus 2 times the square root of 5. And then we're going to square that whole thing. And then add to that the square root of 18 minus the square root of 8, and then we're going to square that whole thing. So we're going to get something like this. Okay, and then maybe to get an idea for how to simplify this, let's do this just one thing at a time. So let's take this green underlined thing first and simplify that. So that's going to be equal to root 5 minus 2 times root 5, whole thing squared. Now what you want to think about is that root 5 and 2 root 5, they're almost like terms, right? It's like x minus 2x, where x is the square root of 5. So you can combine them like they are like terms. And if you've got 1 square root of 5 and you subtract 2 square roots of 5, then you're left with a negative 1 square root of 5. So we can write it like that. So that's like one simplification that we can do to that. So this thing that I'm underlining in purple became this thing that I'm underlining in purple. So if you've got like $1, but you owe your friend $2, then you have negative $1. It's just it's the square root of 5 in this case. Okay, now you square this. Now if you square a negative number, you get a positive number. So the negative's gone. But then if you square the square root of 5, you just get 5, because that's like, the square roots are like equal and opposite of each other. Sorry, the square root and the square is the opposite operation. Now let's do this blue underlined one. So let's see what we get for that. So what's really good about this problem is that this purple or this green box simplified nicely using this kind of like term rule, but this blue one will not. So let's see, we've got square root of 18 minus square root of 8 squared. So now what we want to do is use the fact that this is going to be the square root of 18 minus the square root of 8 times the square root of 18 minus the square root of 8. That's what it means to square something. You just have to multiply it to itself. And then you have to use the distributive rule. So the distributive rule will tell you that you have to do all of these multiplications. So you have to do square root of 18 times square root of 18, square root of 18 times negative square root of 8, and then square root of 8 times square root of 18 like that, and then square root of 18 times square root of 8 like that. So we've got to do all 4 of those multiplications. Okay, so let's see what that gives us. Wait, sorry, this should be, sorry, this one right here should be like that. So there we go. So there are 4 different multiplications. So let's do those one at a time. So the square root of 18 times the square root of 18, that's just going to be 18, because the square roots cancel each other. Then next, the square root of 18 times the square root of 8, well, that really can't simplify very much. That's just going to be minus the square root of 8 times 18. And you'd want to simplify that a little bit, but you know, we're almost out of time, so I won't do that. And then here we have minus the same thing again. So you've really got 2 of them. You've got one of them from this product and one of them from this product. So those add together to be 2 of them. And then finally you have plus the square root of 8 times the square root of 8, but that's just going to be 8. So you're left with something like this. But now notice that those add together to be 20 minus 2 times the square root of 18 times the square root of 8. And this actually simplifies quite a bit. Notice you can take this 18 and write it as 9 times 2, right? And so if you take this 18 and write it as 9 times 2, then you can write this as 9 times 16. But now both of those have square roots. So this is going to be 20 minus 2. The square root of 9 is 3. The square root of 16 is 4. So it's 20 minus 2 times 3 times 4. So that's 20 minus 24. So that's negative 4. 2 times 3 times 4 is negative. Yeah. So notice that we just figured out that this whole thing was 5, this whole thing was -4, which means that this whole thing adds up to the square root of 5 minus 4, which is the square root of 1, which is 1. All right, we kind of rushed through that at the end, but we were running out of time. So we'll kind of pick up and probably do another one that's like complicated like this at the beginning of next time. Hopefully, I noticed that about half of the class, or maybe a little more than half of the class, was signed into the homework thing. You have to get an access code, but I think you have to buy the access code. Like, that's not something I give you. But I think it's reasonably priced, especially since like the book is free or whatever. Hopefully you guys agree with me on that. So anyway, we're out of time, like I said. If you guys need to see me, let me know. I made a Zoom link for my office hours. I'll update the syllabus with that and put that on Moodle later today. I think that's everything.